It's indeed an honor to speak to the students of the Maryland University of Integrative Health, and I want to thank you for the opportunity. My name is Dr. Bill Gurley. I'm a professor of pharmaceutical sciences at the University of Arkansas for Medical Sciences, College of Pharmacy in Little Rock. And I have been doing research on various aspects of dietary supplements for almost 2 decades. And much of that time has been spent in conducting prospective clinical studies to assess the potential for botanical dietary supplements to modulate human drug metabolism. And it's those studies that are the basis for my talk, which is an introduction to pharmacokinetic herb-drug interactions. Now, plants have been a source of drugs since time immemorial. But the issue of herb-drug interactions really didn't come to the forefront until after World War II, when drugs moved from multi-component plant-based preparations to purified single-ingredient synthetic compounds. Now, if one delves into the medical literature, it is obvious that phytochemicals have been recognized for their ability to modulate the activity of conventional drugs for many decades. One interaction most often described is the ability of phytochemicals, or plant-derived chemicals, present in cruciferous vegetables, for example broccoli, and specifically a group of phytochemicals known as the isothiocyanates, to modulate certain drug metabolizing enzymes and thus affect the pharmacokinetics of a few conventional medications. Now, the concern for herb-drug interactions, however, was relatively minimal until 1991. And it was that year that grapefruit juice was found to increase the oral absorption of many drugs and possibly their toxicity. And soon after the grapefruit juice issue came to light, the Dietary Supplement Health and Education Act was passed, and a plethora of unique phytochemicals became available for consumption within the United States in the form of botanical dietary supplements. Now, the issue of herb-drug interactions really didn't come to the forefront until around 1998, and it was that year that an article appeared in the Journal of the American Medical Association. And the article dealt with alternative medicine use in the United States. And the authors of that article noted that in 1997, almost 15 million adults took prescription medications concurrently with herbal remedies or high-dose vitamins, which accounted for about 18% of all prescription users. The authors went on to estimate that nearly 3 million adults aged 65 years or older were also taking botanical supplements concomitantly with conventional medications. And because the elderly are our greatest consumers of conventional medications, then they may be at an increased risk for herb-drug interactions. Now, since that time, there have been a whole host of other surveys that have appeared in the medical literature, some of which indicate that between 30 and 60% of all hospital patients use botanical supplements on a regular basis. And other surveys suggest that between 20 and almost 35% of prescription drug users also take botanical supplements concomitantly. I think one of the most important statistics to take away from this talk is that less than 40% of patients ever reveal the fact that they're using an herbal dietary supplement to most healthcare professionals. And we'll see where that became quite an issue in our institution several years ago. Now, there are a whole host of factors that can contribute to herb-drug interactions, but one of the most common is the fact that many herbal dietary supplements contain multiple herb components. And the more botanicals that you're exposed to, the greater the likelihood that there may be an interaction if you're taking these with conventional medications. You also have to realize that these dietary supplement dosage forms are formulated using concentrated plant extracts. And so the plant is ground up and dried and then extracted with either hot aqueous solutions or organic solvents to concentrate a lot of these unique phytochemicals that produces a greater exposure to these than they normally would if you were just consuming the plant in its natural state. And of course, with regards to these phytochemicals, we really know very little about the pharmacological activity of many of them. A good example I like to use is Panax ginseng. There have been over 500 unique phytochemicals identified in Panax ginseng. And so that alone kind of gives you a good feel for the potential problem when you're taking a Panax ginseng supplement with a conventional medication. And of course, if you're taking a botanical supplement that has a multitude of botanical extracts, including Panax ginseng, then you can certainly see that the likelihood for interactions goes up astronomically. Now, just to kind of continue on with that, this is just a partial listing of some of the known phytochemical constituents in a typical St. John's wort extract. And there are some unique phytochemicals found only in St. John's wort, like the naphthodianthrones and some of the floroglucinol derivatives. And you'll notice that I've got one of those floroglucinol derivatives in the lower left-hand corner highlighted in orange. It's a compound called hyperforin. And we're going to talk about hyperforin in a little bit more detail as we go along. And so, but then again, there are a lot of phytochemicals that are unique to just about all plants, and this includes a number of flavonoids as well as essential oils. And so here again, you can see that with a typical St. John's wort extract, that there's a wide variety of unique phytochemicals that may play a role in modulating human drug metabolism or transport. All right, so how do we initially recognize the potential for an herb-drug interaction? Well, oftentimes one of the first indicators comes from case reports that are published in the medical literature. Now, case reports usually can't establish causation, but they can help generate hypotheses for possible mechanisms. And if you start to see a number of case reports basically documenting the same potential interaction, then there's probably some merit to that interaction. And this also holds true for adverse event reports that are submitted to the FDA's MedWatch program. And of course, if you do a lot of research in this area, you're very familiar with the literature reporting in vitro findings. And in vitro screenings are very useful. Oftentimes they're helpful in identifying potential interacting phytochemicals. And these in vitro screenings typically utilize purified enzymes or transporters or isolated cell lines that express human drug metabolizing enzymes and transporters. And when you expose these enzymes and transporters in an in vitro system to either purified phytochemicals or to botanical extracts, almost invariably, if the concentrations are high enough, you will see some type of an effect. But oftentimes these in vitro screening results rarely ever translate to the in vivo condition. And so to me, the definitive means of identifying potential herb-drug interactions are prospective clinical studies. And that's where most of my research has been focused in the last 20 years. And so the rest of this talk will kind of focus on some of the research from our laboratories. Now, first of all, I want to make it known that there are two general mechanisms for herb-drug interactions. The first one we're going to talk about only briefly, and that's the pharmacodynamic interactions. And this is a situation where a botanical has a pharmacological property either very similar to a conventional medication, which when taken concomitantly may actually add to the effects of the conventional medication and may render it more toxic, or the botanical may have a pharmacological property just the opposite of conventional medication and therefore negate the activity of that conventional drug. And so some examples that you may be familiar with, although the ephedra-containing supplements are no longer on the market, but they can certainly cause hypertension. Same holds true for the ephedra-free supplements. And we're going to talk about the ephedra and ephedra-free supplements in a different talk. A number of weight loss supplements contain licorice extract, and there are some unique phytochemicals found in licorice that can also produce hypertension if taken for a prolonged period of time. And so the ephedra, ephedra-free, and licorice-containing supplements can certainly interact with antihypertensive medications by negating their effects. And another example might be ginkgo biloba, which does have some anticoagulatory effects, and if it's taken with conventional anticoagulant medications, it might exacerbate their activity and potentially cause some excess bleeding episodes. So again, the pharmacodynamic interactions we're going to touch base in more detail in a subsequent talk. So I want to focus now on the next major category of herb-drug interactions, and those are ones that have a pharmacokinetic mechanism. And that means the pharmacokinetic herb-drug interactions are essentially situations where the botanical, when taken concomitantly with the conventional medication, can affect the conventional drug's absorption, its distribution, its metabolism, or excretion. And there are two major mechanisms within the pharmacokinetic herb-drug interactions that are often underlie those mechanisms. This is situations where the phytochemicals can modulate the activity of human drug metabolizing enzymes, and these enzymes are typically found in the small intestine and in the liver. And examples of these drug metabolizing enzymes include the cytochrome P450 enzymes, the UDP glucuronosyl transferases, glutathione transferases, and sulfatases, and there's a whole host of other drug metabolizing enzymes. And of course, the other major category of proteins that may be affected that are involved in pharmacokinetic herb-drug interactions are the drug transporting proteins. Now, these are also prevalent in the small intestine and in the liver and a wide variety of other organs, particularly the blood-brain barrier. And there are two general categories of transporting proteins, and these are the efflux pumps, or proteins that pump drugs out of cells, and a classic example is P-glycoprotein. And then there are uptake transporters that facilitate the uptake of drugs into cells, and these are some examples include the organic anion transporting polypeptides or organic cation transporters, and again there's a litany of these things. So these are just some examples. So again, pharmacokinetic herb-drug interactions are usually situations where the botanicals may modulate drug metabolizing enzymes and or drug transporters. Now, if you're not very familiar with the cytochrome P450 enzymes, these are the principal drug metabolizing enzyme families in humans, and of those, the most important are shown here in this pie chart. And of the cytochrome P450s, the most important with regards to the number of drugs that are affected is an enzyme called CYP3A4, or cytochrome P450-3A4. And again, it's the most important drug metabolizing enzyme in humans because about half of all conventional medications are metabolized to some extent by CYP3A4. The next most important drug metabolizing enzyme in humans is CYP2D6, followed by CYP2C9, and then a variety of others. Now, I want to use this cartoon to kind of illustrate the whole principle of a pharmacokinetic herb-drug interaction, and we're going to use a drug called felodipine as an example. So here we can see that when felodipine is swallowed, it goes into the stomach and then eventually reaches the upper small intestine. And then the cells that line the upper small intestine, the intestinal mucosa, a group of cells called the enterocytes, are often express high concentrations of a variety of drug metabolizing enzymes and transporters. And let's just say, for example, felodipine happens to be a substrate for cytochrome P450-3A4 in the small intestine. And so when it is transported across the intestinal mucosa, some of the felodipine is metabolized. And say of that original dose that reaches the small intestine, and once it crosses the intestinal mucosa, maybe only 30% of the original dose crosses unchanged. And then from there it goes through the portal system to the liver, where it's exposed to even higher concentrations of these enzymes and transporters. And again, some of the felodipine will be metabolized, and ultimately, only in this example, only about 15% of the original dose actually reaches the systemic circulation to elicit a pharmacologic response. Now, if we take felodipine, for example, with a botanical that can inhibit the activity of cytochrome P450-3A4, then less of the felodipine is metabolized as it crosses the intestinal mucosa, and perhaps less is metabolized in the liver. And so that 15% that might normally reach the systemic circulation now increases to, say, perhaps 45%. And so that botanical's effect by inhibiting cytochrome P450 activity can dramatically increase the oral bioavailability of felodipine, and in this case it may render it more toxic and may produce more exacerbated antihypertensive effects. Now, on the other hand, if we have a situation where a botanical induces the expression of these enzymes and transporters, well then less of the drug will reach the systemic circulation, and so that 15% may be reduced to 5% or even less, and so it may render the drug less effective. So that's kind of the two major possibilities for pharmacokinetic herb-drug interactions. And so I want to illustrate that in a little more detail if you look at it strictly from a pharmacokinetic perspective. We're looking at concentrations of drug within the systemic circulation. And so hypothetically, when we develop a drug dosing regimen, we will administer a certain number of milligrams every so many hours. And so if we continue to do that on a regular basis, we will reach what's known as a steady state concentration. And so this diagram shows that the yellow curve just represents an ideal drug dosing regimen such that we eventually will reach a steady state. And those steady state concentrations fall between a minimum effective concentration and a maximum safe concentration. And it just so happens that those concentrations at steady state are oftentimes a function of the activity of those drug metabolizing enzymes or transporters. And so if those drug metabolizing enzymes or transporters are adversely affected, then they can affect the concentrations at steady state. So let's look at the green curve at the bottom. In this case, we have a situation where we have a situation where the botanical is inducing the expression of these enzymes and transporters, and so less of the drug gets absorbed. What does get absorbed is eliminated more quickly, and less drug accumulates, and so it would render that regimen well below the minimum effective concentration, and making that regimen ineffective. On the other hand, if we look at the purple curve, where we have a situation where the botanical inhibits the activity of these enzymes and transporters, well, then more drug gets absorbed. What does get absorbed hangs around for a longer period of time or has a longer half-life, and then it accumulates more. And so the concentrations at steady state may rise well above the maximum safe concentration and render the drug more toxic. All right, so now let's look at some examples of some classic pharmacokinetic herb-drug interactions. Far and away, the most problematic botanical with regards to pharmacokinetic herb-drug interactions is St. John's wort. And you may be familiar that St. John's wort is often used for its antidepressive activity, and actually high-quality St. John's wort is quite an effective antidepressant. It certainly, most of the studies certainly indicate that high-quality St. John's wort products are as efficacious as the tricyclic antidepressants, and even some of the selective serotonin reuptake inhibitors. But the problem with St. John's wort is that it has an extremely high drug interaction risk because it renders most drugs ineffective. Now, I want to share with you some data from our laboratory. This was done back in the late 1990s, early 2000s. And so what I'm showing you here on the left is the effect of St. John's wort on that very important drug metabolizing enzyme 3A4. And our laboratory was one of the very first to do prospective studies on many of the more popular botanical supplements and looking at their abilities to modulate some of the major drug metabolizing enzymes and transporters. And it just so happens that one of the very first ones we looked at was St. John's wort. And so on the left you can see the effect of a 30-day course of St. John's wort on the activity of that enzyme 3A4. The blue circles and lines represent individual subjects in the study, and the red circles and lines just represents the mean value. And what we saw was about 100% increase in the activity of that very important drug metabolizing enzyme over a course of 30 days. And you may think, well, okay, so what? You saw an increase in the enzyme activity. Is that clinically relevant? Well, it just so happens that just a couple of weeks after we finished crunching the numbers in this data set, I got a call from one of the transplant surgeons at our transplant center in Little Rock. And he calls me up and he says, "Hey, Gurley, I know you work with that herbal crap. I got a question for you." He actually used a harsher expletive than crap, but it had the same number of letters, so I think you know what he had to say. Anyway, he said, "Do you think that St. John's wort could interact with cyclosporin?" Now, cyclosporin at the time was a very important immunosuppressive agent that solid organ transplant recipients would receive in order to prevent their organs from being rejected. And it just so happens that that cyclosporin is a substrate for that very important drug metabolizing enzyme 3A4. And so I remember we had just finished that study in the young cohort where we saw that significant increase in the activity of 3A4. And so I said, do you have transplant recipients on cyclosporin and St. John's wort? And he goes, "Yeah, I think we do." I said, "I bet the levels of cyclosporin are really low." And there was a long pause on the phone. And he goes, "Yeah, how did you know?" So what I want to show you here is the cyclosporin trough concentration time profile for a 28-year-old white female who was 5 years post-kidney transplant. And she would come into the clinic once a month and have her cyclosporin blood level drawn. And so you can see these blue circles just represent the trough concentrations. And for the longest time, her levels were within our desired therapeutic range. It's indicated by the broken line there. But around Christmas time of 1999, her cyclosporin levels started to plummet. And we couldn't figure out what the problem was. She was not taking any other medications. She was certainly being compliant. Her levels started to get so low that she started to develop signs of acute rejection. And they increased her dose from 100 milligrams twice a day to almost to 175 milligrams twice a day, which is a very large dose of cyclosporin. Couldn't figure it out. Levels just wouldn't respond. She finally revealed to the dietitian on the transplant team that she'd been taking St. John's wort to help with her depression, and she wondered if that might be what's causing the issue. And that's what prompted the call from the transplant surgeon to me. So once they got her off the St. John's wort, within about a week or two, her cyclosporin levels kind of skyrocketed. And they finally got them back under control. Unfortunately, her acute rejection devolved into chronic rejection, and she lost her graft, and she had to go back on dialysis and back on the transplant list. And this was just one of 4 cases that occurred in our transplant center at about that time. And so when we published our case series in early 2000, literally within weeks after our article came out, there were articles from all over, from transplant centers from all over the world reporting the same thing, that heart transplant recipients and liver transplant recipients and kidney transplant recipients that were on cyclosporin and also taking St. John's wort were developing rejection. So clearly, St. John's wort and cyclosporin interaction is an extremely clinically relevant herb-drug interaction. So what is it about St. John's wort that causes all the problems? Well, there just so happens to be a unique phytochemical present in St. John's wort called hyperforin. Remember I mentioned that earlier. And in the lower right-hand corner is the structure of hyperforin. And what hyperforin does is it binds to a unique protein found in all cells called an orphan nuclear receptor, or it binds to these proteins that are present primarily in the cells that express these drug metabolizing enzymes. And so this particular protein called an orphan nuclear receptor, specifically known as human pregnane xenobiotic receptor, or PXR, when hyperforin binds to PXR, it literally turns on the genes for these drug metabolizing enzymes and transporters and causes the cells to express more of them. And it just so happens that hyperforin appears to be the most potent ligand for human PXR ever discovered. Prior to hyperforin's discovery, there was a drug called rifampin that's very notorious for inducing drug metabolizing enzyme expression, but hyperforin is much more potent than rifampin. And this just, and I mentioned we were talking about the drug metabolizing enzyme 3A4, but it also affects one of those drug efflux transporters called P-glycoprotein. And so this is an example looking at the drug digoxin. Digoxin is not used as much as it once was to treat congestive heart failure, but digoxin is a classic substrate for one of these drug efflux pumps. And its oral absorption is a function of the activity of that efflux pump. And so the black squares represent the concentration time profile for digoxin given by itself with water, and then a 30-day course of either, a 7-day course of rifampin, or a 14-day course of St. John's wort containing hyperforin. And again, the black squares represent digoxin taken with water. The gray circles represent digoxin plus either rifampin or St. John's wort. And you can see that both rifampin and St. John's wort significantly reduce the area under the curve and significantly affects the absorption of digoxin, rendering it less effective. But what I want you to notice is that the curve on the left stems from a 600 milligram per day dose of rifampin, whereas the curve on the right represents a 24 milligram per day dose of hyperforin. So you can see that the hyperforin is much more potent with regards to its effects on inducing the activity of P-glycoprotein. All right, now, so what makes it so problematic? Well, together 3A4 and P-glycoprotein are responsible for the metabolism and transport of more than half of all conventional medications. And it's believed that hyperforin is also responsible to some degree for its antidepressive activity. Now, for the longest time, St. John's wort products were standardized for another compound called hypericin, but it looks like hypericin really has no impact on its antidepressive activity, and it certainly doesn't affect cytochrome P450 activity. So, for the longest time, we really didn't know how much hyperifin were in a lot of these products. Now, since this recognition of the significant interaction, most St. John's wort products are standardized to hyperifin. Now, to illustrate another principle with regards to botanical dietary supplements and phytochemical content, I want to show you some data looking at the amounts of hyperifin from 6 different brands of St. John's wort and the amounts of hypericin. And of course, the hypericin content on the right is fairly consistent because all these products were standardized to hypericin. But look at the hyperifin content. It's all over the map, from as little as 1 milligram per gram to almost 14 milligrams per gram. And so again, just because it's standardized to hypericin, you really had no idea how much hyperifin was in the product. When you start to get around 10 milligrams per gram of hyperifin, you start to see significant induction of these enzymes and transporters. Now, look at product A. Product A1 and A2, that's the same product, but just 2 different lot numbers. And you can see that the amount of hyperifin differs by almost a factor of 4. So one of those lots of that product would have a significant interaction potential, whereas the other one probably wouldn't. And so, again, that's another one of the idiosyncrasies when you're dealing with botanical dietary supplements is phytochemical content variability. Now again, so what makes it so problematic? Well, again, not only does it induce 3A4, but there's a whole host of other cytochromes that it induces, as well as these, a whole host of efflux transporters. And as we've already seen, it can certainly reduce the effectiveness of cyclosporin and digoxin. Other drugs like the anticoagulant warfarin are rendered ineffective. Birth control pills. There have been a lot of miracle babies associated with the use of St. John's wort and taking birth control pills because, again, birth control pills are metabolized by cytochrome P453A4. A host of, a lot of the statin medications to lower blood cholesterol, and a litany of others. Even certain cancer chemotherapeutic agents can be rendered ineffective. So again, that's one of the significant issues with St. John's wort is that it renders most medications ineffective if they're taken concomitantly. Now, I want to shift gears and kind of look at another botanical that acts just the opposite of St. John's wort. And this example is with golden seal. And a lot of people take golden seal to prevent colds and upper respiratory tract infections. But some individuals take golden seal to mask the results of urine drug screens. Now, the interesting thing about golden seal is that for some drugs of abuse, it's actually effective in helping mask the results of the urine drug screen. But for other drugs of abuse, it actually makes them more easy to detect. Now, I'm not going to tell you which ones are effective and which ones aren't, but nevertheless, the interaction risk for golden seal is pretty high. But unlike St. John's wort that induces the expression of these enzymes, golden seal inhibits the metabolism of many drugs because it inhibits the activity of some of these very important drug metabolizing enzymes. Now again, here's some data from our laboratory looking at the effects of golden seal, a 30-day course of golden seal, on the effects of CYP3A4 on the left and the second most important drug metabolizing enzyme, CYP2D6, on the right. And we see about a 40% reduction in the activity of both of these enzymes if an individual is taking golden seal. Now, together, those two enzymes, 3A4 and 2D6, are significantly reduced, and together they're responsible for the metabolism of almost 3/4 of all conventional medications. So you can certainly see the magnitude of the problem if golden seal is present in certain botanical dietary supplements. It looks like there are two unique phytochemicals that are found in golden seal that appear to be the culprits, and these are isoquinone alkaloids known as hydrastine and berberine. And it just so happens that these two compounds are what we call mechanism-based inhibitors of cytochrome P450s. Sometimes you hear the term suicide inhibitors. And what happens is when hydrastine or berberine are metabolized by these cytochrome P450s, the metabolites literally bind to the enzyme and shut it down. And so And the only way to overcome that is to actually produce more of the enzyme. So it's a very potent inhibitory mechanism. This is just the structures of hydrastin and berberine, and I've circled one portion of the molecule of hydrastin with this broken circle, and that portion of the molecule is known as a methylene dioxyphenyl group. And it just so happens that a lot of phytochemicals produce or have a lot of phytochemicals exhibit this methylene dioxyphenyl group because they're actually pretty decent insecticides. And so plants produce these secondary metabolites with these methylene dioxyphenyl groups as a way to ward off insects from eating on them. But it just so happens when we ingest these as humans, they can inhibit some of these drug metabolizing enzymes. All right, and so now, I once got a question in a lecture that I was giving, if there was ever such a thing as a good or a positive herb-drug interaction. And I harken back to a lecture that I was attending one time for the Society of Civil War Surgeons. And I just happened to be a Civil War historian by avocation, and one of my areas of interest is Civil War medicine. And so at this lecture was about quinine substitutes in the Civil War. And during the Civil War, the drug quinine was considered the miracle drug in the mid-19th century because it was one of the few compounds that could actually treat malaria and lower many types of fevers. And so it was the end-all drug to have. And so when the Federal Navy blockaded all of the southern ports, it stopped the importation of quinine into the southern states. And so for those of you that aren't familiar, quinine comes from the bark of a tree primarily in Peru and South America called the cinchona tree. And so quinine was in very short supply in the Confederate Army, and so the Confederate Surgeon General put out an edict to all Confederate surgeons to try to find natural alternatives to quinine from the flora that were in the South. And there was a very concerted effort to try to find plants that could mimic quinine, but they were never very good at finding a true quinine substitute. But what they did find is that if they took golden seal along with quinine, they didn't have to use as much quinine, and the effects lasted longer. And so when that guy mentioned that, I raised my hand up and go, oh, I know the mechanism of action for that. They all kind of looked at me like I was a little bit crazy, but the issue is that quinine is also a CYP3A4 substrate. And so golden seal inhibits the metabolism of quinine because it inhibits the activity of CYP3A4. So I thought that was pretty cool. So there's positive herb-drug interactions have been around for well over 150 years. Now, as I mentioned, there are a whole host of other phytochemicals that express these methylene dioxyphenyl moieties. One we're probably more familiar with is black pepper. You're not going to get enough of these compounds if you just garnish your food with some black pepper, but there are a lot of weight loss supplements that utilize black pepper extract to improve the oral bioavailability of other compounds. And so here you can see some of the piperamides that are found in various piper species, like Piper longum and Piper nigrum, which is also known as black pepper. And so the more classic one is the one in the upper left-hand corner called piperine. And again, these have these methylene dioxyphenyl groups, and they can inhibit cytochrome P450 enzymes, particularly 3A4. And so here's an example looking at the effects of a drug called nevirapine. Nevirapine is used to treat HIV infections, but it also has a pretty nasty side effect profile. And so the curve at the bottom of the open circles just represents the concentration time profile for nevirapine by itself. And then the black squares represent nevirapine plus black pepper extract. And you can see there's a tremendous increase in the area of the curve when nevirapine is taken with the black pepper extract containing piperine. And so again, that can certainly exacerbate the toxicity of nevirapine. All right, now, another example of a pharmacokinetic herb-drug interaction that's a little bit different, and that involves green tea and the antihypertensive medication known as nadolol. Nadolol is what we call a beta blocker. And if you look at the effects of green tea and nadolol, on the left-hand side, we can see the open circle is just nadolol taken with water. And then we'll see the black circles are nadolol plus green tea. And we see a significant reduction in the area under the curve. And so the first inclination might be that, well, green tea is inducing the metabolism of nadolol. The problem is that nadolol is not metabolized very extensively. And so what's going on? Well, it just so happens that some of the components in green tea can inhibit the uptake of green tea across the intestinal mucosa. And so by inhibiting the uptake of green tea, by inhibiting the uptake of nadolol, green tea can render that drug less effective, and it certainly dramatically reduces its antihypertensive effects. Now, the phytochemicals that are present in green tea that appear to be the culprits are the green tea catechins, particularly EGCG. And it just so happens that EGCG and these other catechins inhibit some of these uptake transporters that we alluded to earlier called the organic anion transporting polypeptides. And there's a wide variety of these things, but again, nadolol is a substrate for these in the small intestine, and the catechins in green tea inhibit that uptake transporter and prevent the absorption of nadolol. And again, if there are other drugs that are substrates for these uptake transporters, they too would be adversely affected if taken with green tea. And of course, green tea is one of the world's most popular beverages, and it's also a component of a wide variety of weight loss supplements. Now, just to kind of, I don't want to get you too concerned about botanical herb-drug interactions, because it looks like the vast majority of the more popular botanical supplements don't pose a serious pharmacokinetic herb-drug interaction risk. And there are several reasons for that, and we're going to talk about some of those reasons in an upcoming lecture. But it looks like that most of your very popular botanical supplements don't pose a significant interaction risk. And so to kind of conclude, certainly botanical supplements can interact with conventional medications. The mechanisms may be pharmacodynamic or pharmacokinetic. However, many popular botanicals pose little risk for drug interactions. However, the vast majority of botanical supplements that are on the market really haven't been evaluated in a clinical setting. So the jury's still out on many of them. Now, what is also occurring is that dietary supplement manufacturers recognize that a lot of these phytochemicals are not absorbed to any great extent, either due to poor water solubility or to extensive pre-systemic metabolism across the gut. And so oftentimes they're utilizing new novel dosage forms to improve the bioavailability of these dietary supplements, and those new novel dosage forms may increase the drug interaction profile for many supplements that have heretofore not been a problem. And so that's research is currently ongoing. And so I want to give you a couple of references that you might find useful. A couple that I published a couple of years ago. There's a two-part, very thorough survey of pharmacokinetic herb-drug interactions that you might find useful, as well as another one by some colleagues of mine at Washington State University. And so with that, I will conclude, and thank you for your attention.